This is the video for 10.2 and I believe in 10.3 out of the textbook. So it's mostly covering angles and arcs and how those relate to each other on circles. It's a little bit different than what you've been used to with angles. We're going to actually start calling arcs using degrees, which is the kind of new strange part of this lesson. A few terminology things, central angle, I think we've figured out by now, hopefully. Minor arc and major arc. And just knowing that the major arc has to be bigger than 180 and minor arc has to be less than 180 degrees of the circle. So if you look at this picture on the right, you have a central angle that's 80 degrees, it says, that NRM. The thing that's different now is we're going to start talking about how this part of the circle, let me get a pen, how this part of the circle is the same part of the circle as the central angle is telling us. So we know that this part of the circle is 80 degrees of the 360. Well, we also know that this arc is 80 degrees of the 360 of the complete thing. So we're not really doing distance right now. We're going to be talking about the size of the arc in terms of degrees. So like just what part of the circle is it? That's kind of what you're saying. So obviously if that's 80, then this has to be 100 to cover up 180 degrees, which means the central angle is also 100. Those will always go hand in hand. The arc is 100 degrees, the central angle 100 degrees. If you have half a circle, this is 180 degrees. Well, that's, of course, this is 180 degrees as well, because it's a straight line or half a circle. These are just a review of some of the theorems you've already seen. There's proofs of these, the warm-up proofs that we did. Most of these are on there. Just keep in mind that they go forwards and backwards. You can do they're biconditional. So on this circle on the left, if you know that your arcs are the same, you're going to know that if your chords are the same, which is marked on here, chord, then you're going to know that the arcs are the same. BC and AB would be the same. And you can write that out, like the measure of arc AB would be the same as the measure of arc BC. When we say arc, we're talking about the outside, right? If I say AB like this is congruent to BC, now I'm talking about the chords themselves. So just differentiate between the chord and the arc notation. So either way though, but it's you can go backwards. You can do the converse. If I knew that the arcs were the same, then I would know the chords are the same, and that goes for the same central angles as well. Then the central angles would have to be the same as well. It's all very symmetrical, right? Central angle, arc, and chord all of the same size. Well, the chords we measure in actual distance, centimeters, meters, feet, inches. One on the bottom, this is a theorem, I don't know if we looked at this one yet actually. If you look at the radii are equal, it says on the bottom left here, we're looking. If the radii are equal in length, then the chords that are perpendicular to those will also be equal in length. Also, we already found out from a previous theorem that these would be bisected. So I know CG and GF are the same length, BE and DE would all be the same length. All of those would be the same because the distance the chord is away from the circle is the same. So let me do a little practice thing so you can see what I'm talking about. So let's say I have a radius here, right? So if I'm perpendicular, that's not a very good circle, but if I'm perpendicular to that really close, then it's going to be as big as it can possibly be, or get one of the longer chords that I could possibly have if it was perpendicular. And then as I go out further out to the circle, the chord's going to get a little smaller and a little smaller and smaller and smaller and smaller the further out I go. So the closer I get to the edge of the circle or the circle itself, the chord's going to get smaller. That just makes sense, right? So if I go those same distances out, like let's say I go to this small one and I go way out like that small one was out here, If you're going the same distance out, those chords are going to be the same length, the perpendicular chords. It's just a lot of symmetry, right? Circles are very symmetrical, so that's really all you're kind of putting in your head right now is everything's very symmetrical. If things are perpendicular, that really cuts things in half, like you can see on the right here. You can either go forwards and say, well, if it's a 90-degree angle, then I know it's bisected, or you can do the converse. If it's bisected, then I know I have a right angle here. It's better just to put them into practice. So we have equal chords here on the top left, equal chords. If the chords are equal, that means that those expressions have to be the same as well. So you can immediately just go right in and say, oh, look, chords are equal. That means these arcs have to be equal, which means those have to be the same. And you go ahead and solve, and you get x is 37. You're done. Next problem, it's perpendicular on a diameter. Has to be a diameter. So if it's a diameter and it's perpendicular, I know these chords have been bisected. That's the first thing that comes to my mind. So if DF is 10, that means this is 5 and 5. And it says AF, oh look, AF, I haven't even drawn it in yet, is 13. They want us to find AB right here. I'll call that X. Well, that should look familiar to you. You have a right triangle. I have 5 and I have X on the legs, and then I have 13 as my hypotenuse. That's a Pythagorean triple. I don't even have to do Pythagorean theorem because I got that one memorized, or you should by now. 5, 12, 13, that's a Pythagorean triple. Next problem, same thing. Chords are the same, arcs are the same. Those have to be the same, so you can go right into there. Set them equal to each other because you know they are. And what do we get? 20, 6, 28. Right, 26 is X. They want us to find the measure of arc ED though. So the measure of ED, arc ED, is 4X. But we know X is 26. So 4 times 26, right back where we were, 94, right? No. Oh, 104, sorry. 104. Now keep in mind, this is degrees now. It's an arc. It's not inches or centimeters or anything like that. It's degrees that we're talking about. So if there was a central angle, that central angle would be 104 degrees. Okay, a little practice with the perpendicular bisectors. AB is 12. I immediately know that this is 6 and 6 then, because this is perpendicular here with the radius. DE is 12. I immediately know that's 6 and 6. And CE is 7. CE, where's CE? Oh, CE is the radius, so that goes like that, 7. One thing I'm noticing right away is that the chord DE and BA are the same distance away from the center. Yeah, like so this distance and this distance have to be the same. I know that because AB and DE are the same length, so they have to be the same distance away from the center. So those are the same. Now, is that going to help me? I'm not sure. I don't really need it, it looks like. But if you look on the triangle kind of on the top, we have, let me just call this my x, I guess. So 6 squared plus x squared equals the hypotenuse squared. Square root of 13 is what that is. If they were to ask you, now this of course is CG. So if they were to ask you what CF was, you wouldn't have to go through the whole Pythagorean theorem and stuff again. You would just know it's the same because those chords are the same distance away from the center. But part of this is just getting you used to looking at the radius of the circle and being able to draw that in wherever you want. So in this case, we drew in the radius of the center from C to E to make the hypotenuse of a triangle. And that helps us solve for stuff, right? So just keep that in mind. Now this problem is interesting because there's many ways around to solve this one. You could use isosceles triangles, or you could use the inscribed angles are congruent kind of theorem. Let me show you a couple different ways. So one is noticing that the radii of a circle are all the same. So these are all the same. If that's true, then the base angles would have to be the same. And then from there, you have a triangle that you could find, like that's 50 total there so far. So that means this would have to be 130, right? Subtract from 180. And then you'd have vertical angles. And then you have base angles again, so you'd end up with the 25, 25. So that's one way to approach it. But just keep in mind there was a different way. I know that this angle B up here is subtending this arc, right? If you follow that out, follow the sides out, that's where it's going. If you look at angle C, it's going to the same arc, right? Angle C goes out to the same location if you follow this side out. So this angle has to be the same as the one we had over here because they subtend the same arc. So I could have gone from 25 that I knew to 25 here right away. Now, in the end, it wouldn't have mattered in this problem, but other problems, it's important to notice those kind of things because that might be the only way to do it. But here we have options. These base angles come up a lot. Our base triangles come up, or isosceles triangles come up a lot where you have base angles. So keep that in mind as well. The radius of the circle is very powerful kind of tool. So here's that theorem. It's just kind of formalizing it. We've seen it in a proof. If you look at the warm-up proof number 3, we did a proof of this already. So we said that whatever this angle is, this one would be half the size. So if this was 80, this would have to be 40. And that's because they subtend the same arc over here. This is the center of the circle, so it's a central angle and an inscribed angle. The inscribed angle is always half of that central angle, or vice versa. Same thing over here. It's saying this angle and this angle have to be the same because they are subtending the same arc. So if this was 30, this would also have to be 30. Now these angles over here, I don't know what they would be like up at the top. I don't know what they are. We'd have to figure that out with more information. I don't have enough information to figure that out. But this gets back to the whole idea that it doesn't matter where you put your inscribed angle, as long as it started at the same arc. Let me get a different color. As long as it started with the same arc, then these angles will all be the same. Sorry, that's got a touch. So let's put that to use. They tell us this is 32. I'm immediately, my brain is going, oh, this is an inscribed angle that's subtending BC. Angle A is also subtending BC, right? You can see that shooting out towards BC. So that I immediately know this has to be 32. Doesn't take any time. They tell us angle B is 44. And again, I could go through the whole, there's 180 degrees in a triangle and make vertical angles and work my way through it, but I really just can jump over here right away and say, oh, look, this is 44 as well, because I know those are inscribed angles. Like this, going the other way though, right? Now we're looking, let me grab a different color. So going this way now, right? And looking at this arc, then these two inscribed angles go that way towards that arc. So they have to be the same, 44 and 44. Now what are we looking for? Angle C, well I just found that. So a measure of angle C is 44. AEB, okay, so I do want this one. I have to subtract from 180, but that's pretty easy now. After after I have two angles. So 180 minus 44 minus 32, so that's 76. So it should be 104. Yeah. And on to the big circle. This looks really confusing, but just take it piece by piece and start filling in things you know. We want angles 1 through 5. You don't have to go in order though, so if you see something, just put it down. Maybe I'll list them and then we can start writing them in. All right, so angle, like to me, I see this 100, that's the given. So the angle 3 is the central angle associated with that. So they have to be the same. So that's kind of my first thought is, oh, angle 3 has to be the same. It has to be 100. And if that's 100, it's not a bad idea to write things in sometimes. If that's 100, then I know this is 80. Oh, so doesn't that match angle 5, or arc number 5? That's got to be the same as the central angle as well. Remember, I'm always making sure that this really is the center, because if it's not, that really changes things a lot. So you got to make sure you have the center to begin with. Okay, so those are some nice easy ones. Let's go down the list now. Let's look at angle 1. Can I get that right away or not? Well, if you follow angle 1 out to its arc, I'm just trying to see how big that arc is. I know that arc is 100, so that is known. So this inscribed angle is not going to be the same. The central angle is the same. This angle is going to be half of that because it's the inscribed angle that goes to the same place. So this is going to be 50. And these are all degrees. We're talking about even arc lengths, we're talking about in degrees right now, just saying how much of the circle do we have. All right, if that's 50, that'll give us more information if we need it, but maybe we don't even need it. Let's look at angle 2. Oh, look at angle 2. It does the same thing. It goes to the same arc that we had before. If you follow angle 2 out, and you'll see what I'm doing here with the angle, just follow the sides of the angle out, then you can kind of ignore all those extra little lines all over the place. So just concentrate on that one angle. Where does it go? What arc does it subtend? Well, it's still subtending this 100. So angle 2 is also 50 degrees as well, because it's half of whatever that arc is. Remember, it's the central angle that's the same. The inscribed angle is further away, so it's going to have a smaller angle. It's going to be half. Angle 4 is an interesting one. I kind of like that. This is the same rule. It's the half double rule because it is an inscribed angle. What angle? I haven't used green yet, so I use green. If you follow the sides of angle 4 out, just like you've been doing, and look at the arc that it subtends the whole half of a circle. Well, the whole half of a circle we know is 180 degrees. That's half of a circle. So this must be half of 180. So it's got to be 90 degrees. So that's actually a right angle. Oh, that's interesting. I don't think we've talked about this one yet. I'm going to do a little side thing here. So if I have the diameter of a circle and I try to subtend that, you will always get a right angle. So no matter where my inscribed angle is, it will always be 90 degrees every single time. Oh, that's interesting. Well, it's just a half double rule is all it is, but it's just a specific case of it where you just happen to be subtending half of the circle. So those are all the 5 angles. Not as bad as you think. Take them one at a time. Really isolate what part you're looking at the moment and ignore the other lines. Don't let them all get crisscrossed in your mind, right? Just take them one at a time. And sometimes you just have to start filling in things you know. Even if it's not going to help you immediately, it might help you later on with other things. This one was one of the easier ones, but they do get a little more complicated. But again, if you follow those same rules, you'll be okay. Look for the double half, look for radii, look for the central angle, look for things like I know half a circle has 180 degrees in it, just normal stuff like that. All right, so this is, you can see we're just kind of finalizing theorems a little bit on this one. So we just looked at this half double rule using the diameter. So in this case, it's kind of the converse of that. So I know this is a 90-degree angle down here. So this angle that's inscribed is 90 degrees. So that should immediately tell me that I have the diameter of the circle. This will go through the center of the circle. So this has to be diameter. That's all the theorem really is telling you. If you have a diameter, then this will be 90 degrees. Or the converse of that, if this is 90 degrees, then you will be subtending the diameter. All right, so this on the right-hand side here, this circle is talking about a quadrilateral inscribed in a circle. And that, I think it's easier with numbers to try to explain what's going on. So let me put in a number like if this is 80, let's say. So if I follow that angle out, follow that out to its sides, it will subtend this big arc here. How much is that going to be? Well, it's double whatever this inscribed angle is. So that has to be 160. If that's 160, well then how much is the rest of the circle? The other side of this, how much does all of that have to be then? Well, we have 360 total in a circle, so that would have to be 200 total, right? 200 and 160 makes 360 degrees in a circle. Okay, so this arc is 200. How much would this inscribed angle be? Well, it would be half. That's the rule that we've been following. So this would have to be a half. And you can see that if that's 100 and the other side over here was 80, those are supplementary. And that's the theorem that we're looking at, is if you inscribe a quadrilateral in a circle, right? So this is inscribed, where all four corners of the quadrilateral are touching the circle, then the opposite angles are supplementary. So this 80 and this 100 will always add up to 180, no matter what I started with. I could have started with 50 or 30 or whatever, it wouldn't matter. The opposite angles will always end up being 180. They'll be supplementary. Why? If you think about it, each of these angles are having part of the whole circle. So I have 360 total. One of these angles is going to be half of a part of it, and the other angle is going to be half of the other part. So together, they're making half of 360, which is always going to be 180, no matter how you cut it. And it goes the other way as well. So no matter what this was, if this was 20, I would immediately know this is 160 because they have to be supplementary. All right, so let's use that. So this is a 90-degree angle. I immediately know that's a diameter. QTS, well, that's 180 degrees because that's half a circle because it's on the other side of the diameter. TQR is 28 degrees, and we want QT. We want that. Oh, how am I going to do that? Well, this is a diameter, right? I can see the center right there. So that means that's 90. So if that's 28, this has got to be 62. And if that's 62, this has to be double 62, which is 124. A little fast? Just take it step by step, right? 180 degrees in a triangle, and then you have to use the double rule. So I used two rules on that one. Right? I used the diameter idea to get my 90, and then I used the double rule to get the 124. QRT is 48. QT, oh, that's easy. That's just double, 96. It's really tempting to say they're the same. Remember, it's the central angle that is the same as the arc. The inscribed angle is always half of that. Keep that in mind. ADC, 164. That's a central angle. So that means this is 164 and this is half, 82, which is what you're looking for. This, half, 52 and a half. These are supposed to be quick ones, right? Half double, or if it's the central angle, it's the same as the arc. And this is our quadrilateral rule. So we got 120 over here, which means this is 60, have to be supplementary. If that's 80, this has got to be 100. They have to be supplementary. It's quick when you know the rules. They go really, really fast. And our last slide. This is the end one. So we have a diameter. I can see the center right there. I'm always looking for that to make sure I really have a diameter. We're going to see some problems in the next lessons where we don't have the diameter, and that's really going to be different rules, different problems. Okay, so if that's the diameter, I know this is 90. It's got to be. So x is 15. This one is a challenge problem a little bit. You'll see that the opposite angles have to be, sorry, let me cut this off. Opposite angles have to be supplementary. So you do have an equation that you can write, but the problem is it has x and y in it, so I have two unknowns. Well, let me do the other side, the other set of angles. They also are supplementary, and you're going to see that all of a sudden you have a system of equations. We're trying to get you to use your algebra skills so that you're practicing this while you're doing geometry. That way you're ready for algebra next year. You should know how to solve simultaneous equations. You did this in Algebra 1. So you can do different methods. You can do the elimination method. You can do substitution method. I think elimination method is probably going to be easier in this one. So maybe I want to multiply this by 3 and multiply this one by 2. Actually, we can divide, can't we? I'll multiply. Doesn't matter. There's more than one way to do this one. So 24x plus big numbers, 60, 27, 87. Right? Now, just to let you guys know, there is a feature on your calculator that will solve simultaneous equations for you. I don't like it when you do that. You need to practice these on your own. When you get to Algebra 2, you need to know how to do this by hand. So it's a good idea to practice it now by hand so you're not in trouble next year. Remember, next year you're going to have tests and quizzes where you're not allowed to have your calculator, and you need to be able to do these things by hand. Okay, then you can subtract your equations. So that's going to give us 0, and then we're going to get 45y equals 180. So we can figure out y then, which is just 4, yes? Okay, that really helps out. So if y is 4, this has to be a total of 84 then. And then, of course, if that's 84, then I know this is supplementary to it, which is 96 total. I'm talking about total. You could figure out x from that as well, right? But you don't need to. So 29 times y, what do we got? 80 and 36, 116, right? 29 times 4, yeah. And then subtract 180 from that, 64. So those are all the angles, right? All those 4 angles. Opposite angles are supplementary. Okay, that's it for this video. Yeah, there's more videos to come for each lesson in the circle geometry unit. So look for those. Also proofs, proofs of different things. There's videos for those as well.